Hey, what's going on, everybody? Happy Wednesday. This is JJ. I'm working through a video on physics, and we're actually going to run through those kinematic formulas that in the previous video I said just look up. And you can see I wrote them down here, the four various formulas that you can use when you know that acceleration is constant. And I want to run through this problem up here. Oops, sorry about the focus. That might happen. I'm doing like a makeshift setup here. I'm not at home, I'm actually out of town, but I didn't want to pass up on doing some calculus and physics, so calc-based physics. So our question is regarding Mars, actually. So it has been hypothesized that that life started here on Earth from a meteor meteor shrapnel that came from Mars. So a meteor hit Mars is the hypothesis, and that ejected some of the surface, the impact ejected some of the surface rocks through the atmosphere and out of the planet's orbit. And then that eventually made its way to Earth, and the materials on those rocks or the organic life on those rocks allowed us to have life here on Earth. And in order for those rocks to even make it here to Earth, they need escape velocity of at least 5 kilometers per second. And this needs to occur over a minimum distance of 4, or a maximum distance of 4 meters. And so, what is the acceleration of this ejected material if it were constant? And so we can use one of our formulas to determine this. So what are we given? We're given kilometers per second, so we're given velocity, and that is our v here. And we actually know the initial and ending velocity. So the initial would be 0, and the ending would be 5 kilometers per second. And then we know the change in distance, so from 0 meters to 4 meters. So which one of these formulas makes the most sense? And if I look at them, we don't want anything with time because we don't know time and acceleration. Two unknowns, we don't want to use that. Acceleration and time, we don't want to use that, 2 unknowns. In this one, we don't know acceleration, but it looks like we might actually be able to plug in values for the remaining terms in here. And for this one, we don't know time. We could use this one as well, maybe. So I think we'll use this third one, though. I want to use this third one because we can't use this one actually because this doesn't tell us acceleration in here. We have one unknown, but it doesn't help us answer the problem, which is what is the acceleration if it were constant. So we'll use this third equation here. And by the way, these equations are given. I still haven't decided whether or not they're useful to memorize. Maybe somebody in the comments can let me know if it's useful to memorize these, or maybe just work through enough problems where they kind of come back to memory in a sense, rather than just memorizing them. I do think maybe engineers use these a lot. I don't know. Just let me know in the comments. So we're gonna use this third one right here. And so v naught is our initial velocity squared, so that's gonna be 0. We might actually, we're gonna have to rearrange because we want to know acceleration. So we're gonna rearrange this expression. So I'm gonna rewrite it. So we got v squared in the x direction. So velocity squared in the x direction is equal to the initial velocity in the x direction squared plus 2 times the acceleration in the x direction, or along the x dimension, and then we have our change in distance, our displacement. And so if we rearrange for acceleration, we're going to subtract our initial velocity from our final velocity. So we get v squared along the x dimension minus the initial velocity squared along the x direction. And that equals 2 times our acceleration change in velocity. And I might have to run out of room at some point. I'm gonna to start trying to write smaller. So then I might have to erase things, which I don't want to do, but I might have to. So then let's divide both sides by the change in x, so displacement, change in x. Again, it might go out of focus, I do apologize. I'm working as best I can with the equipment I have. And so this new expression, this new equation we have is the initial velocity, the final velocity minus the initial velocity squared over the displacement. And that equals 2 times our acceleration along the x dimension. And so with that, we can plug in our givens. So our given is change in velocity 0 and 5. So final velocity is 5. And so this is in kilometers, and then this is just in meters. So let's just make this meters per second. So 5, convert that. Kilo means 1,000, so really it's 5,000 meters per second squared minus 0 over 4 meters, right? 4 meters, up here 4 meters. 4 meters minus 0. So our final minus our initial, and this all equals 2 acceleration along the x dimension. And so 5,000 squared, 5,000 squared is 25, and then 3 zeros 3 more times, so we have the 5,000 and then another 3 zeros, and so we get 25 million meters squared, seconds squared. So remember, when we square anything in physics, the units are also squared. And so that's minus 0, and then we divide that by 4 meters, and we get 2 AX. And so 25 million divided by 4, I don't know what that is, let's plug that into the calculator. 25 divided by 4, what is that? I did times 25 divided by 4, 6.25. So this is 6,250. Hold on. 25 million divided by 4. 6,250,000. Sorry. This is equal to 6,250,000. And our m's cancel out, so we just get 1 meter, and then we still have seconds squared. And this equals 2AX. We divide this by 2, we get 3,125,000 meters per second squared equals our acceleration. Okay, so we just did all those calculations to get our acceleration, which was our first question. What is the acceleration if it were constant? It is going to be 3,125,000 meters per second squared. And then we can also write this in G's. So the G force. And the G force, Jesus, I hope that wasn't out of focus the whole time. G force is equal to, it's going to be our gravitational constant, so that acceleration for gravity, which we'll say is 9.8 meters per second squared, and that equals 1g. So if we divide this by 9.81, Basically, we can say this is 10 just because it's easier on us, and we get rid of a 0. We get, this is going to be 312,500 G's, right? Yeah. And so we can actually quickly answer question C here. It says that roughly, and this is based on experimental evidence, roughly 40% of bacteria, called Bacillus subtilis, I think, survived 450,000 Gs. And this is only 312,500 Gs. So can we reject the hypothesis that we are actually from Mars? Based on this information and data, we cannot reject the hypothesis. So the answer here is no. We cannot reject the hypothesis, the null hypothesis. The null hypothesis is that we are Martians. Okay, and so the acceleration we got to be 312,500 Gs. Okay, but we didn't answer part B. How long would this acceleration last? Let's say last. How long would this acceleration last? Well, now we want to use an equation that has t in it, because we need to solve for the time. And I think this first equation looks adequate. So now we know the acceleration, we know our velocity. So we'll use that equation. We would plug in the values, solve for t, and we would get how long would this acceleration last. And since I'm out of room and I feel like this video is long enough, I think you get the idea. Again, we would just plug in what we've already accounted for and what we've already solved for. Just plug it into this equation and solve for t. Solve for t. And then we would get the time of how long this acceleration lasts. Yeah, and with that, we will see you in the next video. All right, bye.